Hi, so today we are going over decomposition of matrices, and we're starting with an easy case. We already talked about diagonalization. So this was pretty neat because what we did there was we had a matrix, let's call it A, and we could describe it by three other matrices essentially. This was the matrix P. There was a matrix D, and there was a matrix P minus 1. So this is the inverse of this one. So actually what we did here was we have this thing here, and this is basically the transformation, the same transformation that this thing here is. So basically we have P here. This just contains the eigen vectors of this transformation. And the interesting thing about this is the column vectors, the eigenvectors here, get scaled by D. We know D contains the eigenvalues. So the only thing we do here, basically, is we scale these eigenvectors. So we had something like, let's say V1, V2, V3. So we had these three eigenvectors. The only thing we did here, we had this other diagonal matrix that had here the eigenvalues. And there was nothing, so that's why it's called diagonal, because it only has values in the eigen on the diagonal. And when we computed this, we got basically only this one, this here scaled. So we got lambda 1, we got, so this is column vectors, don't forget that, this is column vectors inside the matrix. And the only thing we got is we got this column vectors scaled by the eigenvalues. And so this is ugly. So too long for a matrix, but you get the idea. You just get this thing here multiplied by the eigenvalues. Okay? So this thing represents the transformation A in the basis of the eigenvalues. And what we can do now is this transformation, we can use this thing here to transform it back into our basis, in our standard basis. And we have something really neat here, the diagonal, and I want to show you what we actually can do with it. Just remember one thing. This thing here is the eigenvectors. They get scaled by the eigenvalues, and then this transformation, that's just in another basis, gets transformed back into a standard basis of A. So this transforms into standard basis. Standard basis. So that's what we did last time, and now there's a really cool thing we can do. So we talked about we have this D, we have P, we have D, and we have P minus 1. And actually, what we would like to get is something that maybe tells us, like, what are the effects of Q1, of Q2, and Q3. Something like that could tell us, like, well, this happened by Q3, this happened by Q lambda. So we want to somehow decompose it. So we have maybe a component A, a component B, and a component C, and they all get transformed by these eigenvalues. And what we're talking about here is decomposition. And what we can do with it is we can use it to reduce dimensionality, or for topic modeling, so we use it for unsupervised learning. So I will say decomposition now, because this is actually what we want to do. So, unsupervised learning, because first thing we can do is we can decompose into different parts of our transformation. So maybe some are not so important, so we can reduce dimensionality. And this is important. The other thing is also that we can do some topic modeling. What we will do in the coming weeks. And what I really want to say here, if you really want to get something like that, where we maybe say, well, this lambda, the first one, has a high value, it is 10. And this other lambda here, maybe it's -3. And this one is only 0.2. So if you think about it, this one actually really contributes much to the transformation. Right? This is a high eigenvalue. It actually is important. This one is less important, and this is close to not important at all. So if we would like to reduce dimensionality, we would just take this part away. Maybe it's just noise. Maybe we would also think about taking this part away, but for sure we would keep this part here. This is important. And so now what we can do, we know the diagonal looks something like that. So this is for a 3x3 matrix. Doesn't really matter how big it is. The only thing that matters is that it is square. And we can think about describing this thing here actually as, well, this is the same thing as having 3 matrices. So let's consider everything else 0. You have a lambda 1 here, you have a lambda 2 here, and you have a lambda 3 here. So everything else here is 0. Yeah? Everything is 0. 0, that's 0, 0, 0, 0, 0, 0, 0, 0, and so on. Now, something interesting happens. What happens if we actually multiply these things together? And I will show you that on the right side with the example of this one here, because it's the same thing for everything. So P can be described as having this 3 vectors, P1, let's call it P1, P2, and P3. We know what this is. This is just the eigenvectors, linear independent eigenvectors of our transformation. And then we say, well, we take this thing here, and we just, well, we can say this is the diagonal, so let's call this D1, D2, D3. I just want to show you an example. And we now matrix multiply this with this thing here. And the interesting thing that now happens is, if you think about it, this thing here matches with this thing here, and this thing here matches with this thing here. So actually those two cancel out, because they're only 0, 0. So you can cancel those out. And then the last one actually works out like that. So what happens here is that we can do the following thing. We compute this thing with this values. So we get here, this thing here, basically, this is our result. So we just get this thing here, and this is 0. So this is just lambda, the eigenvalue times the eigenvector. This is what we had before already. I think somewhere I erased it. But basically, what we get here is just this vector here. So we don't have to think about this other vector. And then, what we can do here on the other side is we have 3 vectors, again. And this is the inverse now. Okay? And we will talk about the column vectors here now. So this is P inverse. This is the first vector, that is the second vector, and this is the third vector. And now, again, we match this thing with this thing here. We match this thing with this thing here. We match this thing with this thing here. So what happens is we don't have to think about those two. And what we get, if you think about this, is something that looks like this thing. So we had P1 lambda. We can just pull out the lambda, do something like this, and we have something like this. And now, last time, I think, or the term before that, we talked about shapes of transformation. So we know this here has a shape of. So let's think about the shapes. Well, let's do it here. So this here has a shape of, let me say this is 2, 1. And this is 1, 2. Or no, it was 3, sorry, because we had 3 here. So 3, 1. This is suddenly it's 3, 1. And here we have 1, 3. So what we see here is that the inner dimensions, they are matching. That's fine. And what we get as an output is the outer dimensions. So this thing gives us actually our component that has some values in here. I don't know which ones. We have some values here. 9 values here. It's a 3 by 3 matrix. And this is what we could here call our component A. And let's call this A. We also have the lambda here still. So this is lambda 1 times A. So what we can actually do here is we can decompose our matrix into different parts. But this thing here is just a matrix. So it's a full linear transformation we have here that we can use. And this is not the same thing as the inner product, the dot product we talked about before. So if we have something that looks like this, we have these two vectors. They basically, we can put one vector here, like one vector here, the other one here. This is the first vector we multiplied with. This was P1. This was P inverse 1. And we get this shape here. This is important, don't forget this. The thing we did with the dot product was the opposite. It was, we did not do that, but we had something that looked like this here from the shape, and this here from the shape, and then we get this here. So this was side length 1, 1, 3, 3, 1, 1, and then we just matched 1, 2, 3 elements here. So this element, I don't know, let's call it. We basically matched those elements here. This with this, this with this, this with this, then we got some number here. So that was everything I actually wanted to talk about. And obviously, just to clear up what we did here, is we computed the first component here. For example, if it has an eigenvalue of 10, this means it's much more important than the other components, and we can actually then say we reduce the dimensionality of the thing by, for example, erasing this thing. And this actually means if it was rank was full rank before, so A, let's say A is full rank, it doesn't have to be. If it would not be full rank, one of those eigenvalues would be 0, but let's say it's full rank, it has 3 eigenvalues that are non-zero. That means 3. Then afterwards, it would be, if we take only one of those parts, we'd call this part A, so this is a little bit confusing. Let's make a little hat on here to say that it's something different. If you take this thing here, and only use this thing here, then it has rank 1. So what does it mean? This means our columns are actually linearly dependent. And if you think about it, what we're doing here, let's do a simple example to finish up. We have something, and we actually dot it with, we don't dot it, we take the outer product with something else. Doesn't really matter what we have. Let's say we have 1, 2, 3 here as well. Does not matter in this case. What we actually get is we get this vector 1 time. So we get 1, 2, 3. Then we get this vector we get it 2 times. So we get 2, 4, 6. And then we get this vector 3 times, which is 3, 6, 9. And this thing clearly is linear dependent, because if we have this thing here, v1, v2, v3, well, I could say this is just 2 times v1, and this is just 3 times v1. So we are composing, and we reduce the dimensionality. That's what we did. And in the first AI course, we will do stuff like this. We will do stuff like this with non-square matrices. It will be more powerful, but what we already can do is we can decompose square matrices that have a full set of eigenvalues and or eigenvectors, and we can actually reduce dimensionality, and this will become very powerful in the next weeks. Thanks. Took some time.